Hello everyone. Welcome back to the next lecture of quantum mechanics. So in today's lecture, we are going to, discuss one of the most fundamental concept in quantum mechanics, that is the wave function and the physical interpretation of Schrodinger equation. So in previous lecture, we studied the, Schrodinger equation and, understood that solving the equation gives us a quantity that is called as the wave function, and that is represented by psi of xt. So, but an important question arises here that what exactly this wave function is and what physical meaning does it carry? So unlike classical physics, where quantities such as displacement, velocity, kinetic energy, linear momentum, the potential energy or total energy, or electric field have direct physical, interpretation. But the wave function in quantum mechanics is not directly measurable quantity. Instead, it is a mathematical function and that contains some informations about the quantum system or, a state of the quantum system. In today's lecture, we will understand what the wave function actually represents, why it is generally a complex function, what condition of physical, acceptable wave function must satisfy, and how Max-Born statistical interpretation connects the wave function with probability. So we'll also discuss, concepts such as normalization, continuity, and a boundary condition, and the physical acceptable versus unacceptable wave function. By the end of this lecture, you will be able to understand how quantum mechanics shifts our, description of nature from exact deterministic trajectories to probabilistic interpretation. So let's begin with this lecture today. So here you can see over the screen the Schrodinger equation that contains various parameters that already I have discussed in my previous lecture. That is m, t, x, psi. Psi is very important, parameters for the Schrodinger equation. And once we solve this Schrodinger equation, we get the value of psi of xt. Is that clear? So this is not a physical quantity, but contains some informations about the particle. So in that sense, it can act as a computational tool rather than a physical wave like sound wave or water wave. So, however, this wave function psi of xt, contains some informations about the particle and the system. Otherwise, solving the Schrodinger equation would not serve any purpose. So the important point is that the wave function does not, in fact, corresponds to any measurable physical quantity. So to extract any physical informations from this wave function, you have to operate an operator over this wave function. And then once you operate the operator, like in previous lecture, we have already discussed about, we already understood about, what is linear momentum operator, kinetic energy operator, total energy operator, that is called as a Hermitian operator. And then we also studied about the position operator. So once you operate this operator over the wave function, then you will be able to extract that observables, that is the meaningful physical quantity, right? Okay. So as I have already told you that wave function is the complex function and that will contains both the real and imaginary part. So that's why this is called as the complex function, complex physical function. Now coming to the criteria of the wave function, it's very important. So based on this criteria, you can select some wave function, whether that any function is coming in the range of wave function or not. So first criteria is the wave function must be finite and the single valued and continuous. We'll see these things using the graph as well, right? Next criteria is the derivative of psi xt must be finite, single valued, and continuous. Like del psi by del t or del psi by del x should be finite. Why I'm talking about these things? Because when we calculate or when we operate an operator like the linear momentum operator, so linear momentum operator contains the derivative term, or the kinetic energy operator contains the double derivative term of the wave function. So that's why if the wave function will not be finite, then you won't be able to extract the measurable quantities from that. So that's why the wave function must be finite, single valued, and continuous, and the derivative should be also finite, single valued, and continuous. That is very important point for the wave function. That is the psi xt, that is the wave function must be normalized. That is, if you integrate the wave function from minus infinity to infinity psi of xt dx, that should give you a finite value. Next point is that for a bounded system, let's say if x tending to infinity, psi of xt should be zero. That is called as the bounded system. and the wave function must satisfy the boundary condition, right? So here you can see that wave function must satisfy boundary condition. If you define the physics of the problem, and then the wave function is coming, then that wave function should satisfy the boundary condition as well. So that we'll see using this graph. So in this slide, I'll be talking about, the acceptable and unacceptable wave function. It's very important criteria to understand whether the wave function is acceptable or unacceptable in the quantum mechanics or not. So here you can see in the first graph, basically, you can see on the x-axis, this is a position, and on the y-axis, there is a wave function. And if you see it when x tending to zero, it is going to asymptotically, it is becoming infinite, and it is making an asymptote. So when x tending to zero, so basically what happens, this is not a physically acceptable because of if you calculate the probability density mod of psi x square, and it will be infinite, and infinite probability has no physical meaning, right? So that's why this wave function is not acceptable, right? Now coming to the second wave function. So in this plot, if you see here, so at a particular value of x, this wave function, have three different values. So at a particular instant, a particle cannot have three, that means this is not acceptable because the probability of finding a particle at one location must be uniquely defined. But here you can see the probability of particle of finding is not uniquely defined because particle is at a particular position. There are three probability that you can calculate. That is not acceptable also. Now, coming to the third graph here, you can see that at a particular value of x here, this part psi xt is jumping from one value to another value, right? And that means this is a discontinuous wave function. It suddenly jumps from one value to another value, and this is also not physically acceptable because the derivative becomes discontinuous. That is the second criteria for the wave function, if a function will be wave function or not. And becomes derivative becomes discontinuous as well, and the Schrodinger equation cannot properly describe the system. That's why this cannot be a wave function, and that is an unacceptable wave function. Now coming to the fourth one, that is at x equals to 0, this is finite, but when we are going away from the origin, it is becoming infinite. And if you normalize this things, it will give you the infinite you cannot normalize because area under the curve will give you the infinite value, and that's why this wave function is also not acceptable. Okay, so these were the examples of acceptable and unacceptable wave function, and this type of wave function satisfied all the physical condition, I mean, uh, that we have already seen. So from these examples, what we learned that the wave function must remain finite, continuous, single valued, and physically normalizable, as well as that is applicable for the derivative as well. Okay, great. Now, coming to the next part of today's lecture, that is the normalization of wave function. It's also a very important concept, and this concept we will be using when we will be, driving the particle in a box in 1D and 2D. There you will understand what is the physical or why this normalization is important for the wave function. So when we talk about the normalization, that is according to the Born, statistical interpretation that we have already seen in the previous lecture. So psi of modulus of psi of xt square, that is equals to 1, right? This criteria we have already seen in our previous lecture. So that basically, this criteria basically represents the probability density of finding the particle at a position x and time t. So therefore, if we integrate the probability density over the entire space, we should obtain the total probability of finding the particle somewhere in the universe, right? So that's why the total probability must, always be equal to 1. So that's why mathematically, if you see, if you integrate these things from minus infinity to infinity, psi of xt, modulus of psi of xt squared dx, that should give you the value 1. So this condition is called as the normalization condition, right? So now, if we see this graph here, if we plot, modulus of psi of xt squared on the y-axis and position of the particle on the x-axis, but in this kind of graph, you see that if you calculate this value, that is going to be infinity, right? So The shaded area represents the integral of probability density. It should be a square here, mod of a square. I have forgot to mention, but you try to understand what I'm trying to tell you here. So if the condition is that if the area becomes infinite, then the total probability, also become infinite, and which is physically impossible. So therefore, such wave function are rejected, right? So this wave function is not physically, uh, not physically fulfilling the criteria for acceptable wave function as well. So psi xt must be normalized. That means minus infinity to infinity. If we integrate these things over the psi of xt dx, that should be finite. Now, coming to the next graph, it's also very important. So here you can see that this wave function basically oscillates between, across this domain, across the x domain, right? So, and also, but its amplitude remains finite. If you see here, it is bounded, and if you calculate the total area under the total area, so the probability density curve remains finite. It won't be infinite anywhere else, right? So then the wave function can be normalized. So you can normalize these things very easily, and normalization is so that is fulfilling the criteria for acceptable wave function. So if it is sinusoidal or something like that, then that it's comes under the acceptable wave function criteria. So here what we have seen, that normalization is extremely important because it allows us to interpret the quantum mechanics probabilistically. So without normalization, what will happen? The probability lose meaning. So that means measurements cannot be interpreted physically, and the wave function no longer represents a valid quantum state. So thus normalization forms one of the most fundamental requirements of the quantum mechanics, right? Okay, so I'll stop this lecture here only. In today's lecture, we have seen that physically acceptable and unacceptable wave function and how we can normalize the wave function and why normalization is important, right? Okay. So in the next lecture, I'll start discussion about the particle in 1D box, and then we'll go to particle in 2D box. Okay. Thank you. Stay tuned with the lecture. If you have any doubt, you can put in the comments. We'll see you in the next lecture. Okay? Thank you.